So this is homework 5 part B, where we are going to solve for air and water flow through a cooling tunnel. So let's first draw this. So this tunnel has air flowing into it or water flowing into it and out of it. And then has air flowing in through the bottom and air flowing out of it through the top, because there's a fan cooling the air going upwards. And it also has a section of packing to increase the surface area and volume of the air and water interaction. And this packing, we're going to call it the area of lowercase a, has units of meters squared over meters cubed, which is the surface area over the volume, the surface area of the packing over the volume of the tunnel. And to solve this equation or this problem, we're going to be looking for 3 equations, which are the difference in temperature of the water over the position. We're going to be looking at the difference in temperature of the air over the position. And finally, do this one purple, the concentration of the water, vapor, and air over the position. All right, so first we're going to define the packing. And the flow rates of the water and the air. So like we said, water was flowing down. And air is flowing up. And this length is, we're going to define as dz. And I'm going to also define this as the positive direction. So the flow rate of L is going to be in meters, not in meters, kilograms per meter squared per second. And the flow rate of air, we're going to define as G, and this is going to be meters cubed per meter squared per second. All right, so now let's go into defining the equation for the temperature of water through dc. So this equation is going to be the flow rate of the liquid, or of the air, not the air, of the water, times the heat capacity of the water, times the area, times the difference in the temperature of water. And this is going to be equal to our heat transfer and mass transfer. So our heat transfer is the area of the packing times the area of the tube times the heat transfer coefficient times the temperature change from the water to the air. And then this is all over through dz plus now our mass transfer, which is lambda times the area of the packing times the area of the tubing times our heat transfer or mass transfer coefficient times the the concentration of the water minus the concentration of water vapor and air, the air concentration of air. And this is through dc also. So let's define some things so we can simplify this equation further. So the concentration of water we know is going to be concentration of pressure saturated over our temperature of the water. And we can find this pressure saturated through Anton's equation. And then we also know that the relationship between heat transfer and mass transfer is the heat transfer coefficient is equal to the mass transfer coefficient times density times the heat capacity. And then this is also equal, the heat transfer coefficient being equal to the heat transfer coefficient divided by density times the heat capacity. And we're going to put all of these equations into units of the heat transfer coefficient. So we're going to be getting rid of the mass transfer coefficient. So this equation then simplifies down to the area of the packing times the heat transfer coefficient divided by the flow rate of water times the heat capacity of water multiplied by the temperature of water minus the temperature of air plus lambda A H over the flow rate of water times the heat capacity of water Perfect. So now let's move over to the concentration through dz. So this is then equal to the derivative of the flow rate of air times the area times the concentration, then equal to the area of the packing times the area of the tubing times the mass transfer coefficient times the concentration of water minus the concentration, and this is all through dz. So then this now simplifies down to the area of the packing times the area or the heat transfer coefficient all over density times the heat capacity of air times the flow rate of the air plus multiplied by the pressure saturated, R, temperature of water, minus concentration. All right, and now finally, we're going to go through the temperature of the air through dz. Now, this equation is the derivative of density times heat capacity of the air times the flow rate of the air multiplied by the heat capacity of the air times the temperature of the air minus the flow rate. Oh, I think I forgot. Did I forget to put that up there? Oh, no, I didn't. The enthalpy of vaporization over density times the concentration, and this is then equal to the heat transfer minus the mass transfer All right, and now this then simplifies down to simply just the area of the packing times the heat transfer coefficient over density times the heat capacity of air times the flow rate of air multiplied by the temperature change of water, or the temperature of water to the temperature of air through dz. All right, and now we're gonna go into Excel and use the differential equations that we just created to compare the cooling tower height necessary for each inlet condition, which different inlet conditions of temperature. So this is homework 5. Hi, this is homework 5, part B, where I'm going to be calculating and finding the temperature of water exiting the cooling tower. So let's get started. Oh, and you're going to see me looking down here, which is my iPad, which has all the equations that I calculated. I put it on the screen, but it's very small to the best of my ability. So let's first calculate for the density of air. So this is the molecular weight multiplied by 103.25 divided by our gas constant R times the temperature of air. Yes. Alright. Now our concentration of air saturated, which is going to be Anton's equation, minus B sat C sat plus T1 minus 273 times our 5 and then this is all divided by our it's a plus air, T air. Alright, and now our concentration of air is equal to concentration of air saturated. The concentration of vapor in air is equal to the air saturated times the humidity, relative humidity. Alright, and now we're able to calculate our mass transfer constant, which is our heat transfer coefficient divided by our density of air times the heat capacity of air. Perfect. Alright, now we can go into our setup calculations. So this is going to be our counter, our DZ, and then we're going to do our concentration, our temperature of water, our temperature of air, our pressure saturated, and then our equations. Alright, so our counter goes from 0 series step value 1 all the way to 1,000. Oh, I forgot to do it as a column. Alright, and then our DZ, our step value, is equal to this times our step, and then that should be equal to 5, yep, at the bottom, because our tower is 5 meters tall. So our concentration at first is equal to the concentration of air alright, and then our temperature of water is going to be equal to our guess, which is, we think that the temperature of the water and air are going to be equal, that we're just guessing that initially. Temperature of air is equal to temperature of air. Our pressure saturated now is equal so our pressure saturated is equal to our Anton's equation, B air divided by C air plus the temperature of air minus 273, because we have to turn it back into Celsius, multiplied by our conversion. All right. And now the really fun, not so fun part. So now we're calculating our equations. So, okay. So this equation is equal to our A times our H times the difference divided by our flow of the water times the heat capacity of water all right, plus our lambda times A times H divided by our flow rate of the water times the heat capacity of the water plus 1 over the flow rate of the water times the heat capacity of the water times our pressure saturated. Yeah, pressure saturated divided by R times temperature of the water minus C. That is not right. I forgot to calculate our concentration difference. And the concentration difference, so yeah, our concentration difference is pressure saturated divided by our gas constant divided by our temperature of the water minus our concentration. Now we can go ahead and calculate our okay. Now we can calculate our C, which is our packing area. Oh, and we're also going to do these for simplicity through our mass transfer coefficient instead of typing out the whole long equation. Makes it way simpler. So it's going to be our mass transfer, or times our mass transfer coefficient divided by our flow rate of our air. Times our concentration difference. And now our T, our air, is also going to be in units of our mass transfer coefficient. So it's our packing area times our mass transfer coefficient divided by our flow rate of our air times our temperature difference. All right. So now we're going to use Euler's law for this, which is where you were plus where you've been times your, so again, where you were plus the increment times, right, equals where you were plus increment times, right? Yeah. All right, and then we can bring these down. Perfect, and now we can bring these all the way down. Okay, perfect. So things start to get crazy. So yeah, this is gonna be the top of the tower. Forgot to define that earlier. So yeah, things get crazy because the temperature has to increase for mass to be transferred. Whoa. So now we're going to adjust, and then this is the bottom. So now we're going to adjust and use our solver. So it was what? Equal H2O3? No, it was 202. Cool. All right, now we're going to find the sum squared. So it's R minus squared. Okay, now we want to minimize this with our solver. Data solver. And then we're going to change the value of this. I don't know why it does that. Okay, solve. Cool. Okay, and now let's see. Temperature of the water. So we wanted it to be equal. Okay, so yeah, that's right. And now if we increase our humidity, in theory, if we increase humidity, then there'll be less mass and heat transfer. So let's increase this to 50%. So let's see. So yeah, we've seen that the temperature of the air actually went down because if there's so much more humidity, then it won't take as much energy and mass and heat transfer to increase or decrease the temperature.